Firstly, let's talk a little bit about the thermal effect on the axially loaded members. When a piece of material is heated, it will undergo the thermal expansion, and similarly, when a material is cooled, it will undergo the thermal contraction. Therefore, under the change of temperature, we will introduce the thermal strain, which is the axial strain due to the thermal effect. The thermal strain is given by the thermal deformation divided by the original length, so it is rather trivial. But we will introduce a new constant which is related to the thermal effect, which is alpha. So the alpha is called the thermal expansion coefficient. Therefore, we can say epsilon t, which is a dimensionless quantity, equals to alpha times the change of temperature. That means the axial strain equals to the thermal expansion coefficient times the temperature. Notice that the thermal expansion coefficient has a unit of degree to the power minus 1. So in the later examples, you will see it is look like something like 1.7 times 10 to the minus 7 per degree. So you can see something like that. It is the thermal expansion coefficient. And significantly, after you have this coefficient, you times it with the temperature. Then its unit will become 1, which is the dimensionless form. At the same time, we rewrite the right hand side of this equality. Then we can find the thermal deformation, which is the axial deformation caused by the change of temperature. It is given by the thermal expansion coefficient times its original length times its change of temperature. So as we just described, when there is a change of temperature on this piece of material, then there will be free expansion or contraction, right? The ball will have the thermal axial strain. Also, the change of temperature can be either positive or negative. Also, we will assume the change of temperature over the entire member is uniform. So we won't say, okay, this tip is very hot, while this tip is very cold. So we don't consider that consideration. So we don't consider that case. So we consider the change of temperature is uniform over the entire beam or the entire bar. Consider a piece of material with both sides clamped now. So instead of letting it expand or contract freely, we will fix both ends so that no matter how, I repeat, no matter how the temperature changes, there will be no change of length over the entire section. So how does it work? So when the piece of material is heated, it will become longer, right? But by applying a force on this end, we can put this elongated bar back to its original length. Similarly, when it is under cooling, when it is contracted, the length of the bar will become shorter. What we do is to apply a force that pulls it back to its original length. So this is the reason why we consider the bar under the clamped condition, because under such condition there will be axial force, axial load, and consequently the axial stress acting in the cross-section of this beam. Consider the case of heating. Well, it is rather similar to cooling, but we just try to understand this case, then we can extend our knowledge to the cooling concept. So consider this bar is being heated, and there will be positive axial strain, the thermal axial strain. By applying a clamped wall at the end of this bar, it prevents the bar from expansion. However, it will act a compressive load on this bar in order to put this bar to its original position. So we can write the axial strain caused by the clamped end is the negative of the thermal strain. What does that mean? That means the bar is elongated by the thermal expansion, the positive temperature change, right? Then, as I am a clamped end, I must try to push you back, apply a compressive stress on you, right? After you apply the compressive stress, then you will pose a negative axial strain over this entire region. Therefore, we can say the axial strain caused by the external load equals to the negative of the thermal strain. So what is the axial stress caused by the clamped end? We know stress equals to the Young's modulus times the strain. Now the strain is the negative of the thermal strain. Then we will make the substitution. E equals to, so still remember the thermal strain equals to alpha times the change of temperature. Therefore, the stress equals to negative of alpha delta T times E. Similarly, for the axial force, you just times the area of the cross-section over the stress, then you will get minus of alpha delta T E. So those part is completely the same, right? And then you just multiply it by A. So I repeat, the axial stress equals to minus of alpha times delta T times the Young's modulus, while the axial force equals to minus of alpha times delta T times E, and then you times its cross-sectional area.